Okay, so let's begin by looking at some numerically computed solutions to this cosine oscillation problem, the simplest second order differential equation. And so that differential equation is simply y double prime equals minus of y, or I should say that in the plot here this symbol u is basically y. And so we discretize, we rewrite this as system of two first order equations, and we discretize. And so here we're looking at results that were obtained using first order Euler. And as you can see, the symbols here in the red plus signs are the exact solution that we are comparing the numerically computed solution for. And so there are three step sizes that are used, and so in terms of the number of steps over the interval up to 2 pi, this is 2 pi, and we're using a number of steps equals 10, 20, and 40 as we carry out that integration. And so you can see something very troubling here, that this solution which is obtained with 10 steps, this is with n equals 10. You can see that instead of oscillating between +1 and -1, this thing is growing in its amplitude as we go to larger x. And that behavior is continuing as we refine the step size. And so when we go to 20 and when we go to 40, we still have this growing oscillation. The magnitude of net growth over the interval up to 2 pi has been reduced, but there is this intrinsic growth of error behavior, unlike the physical solution that this particular method builds into the algorithm. And so it's not a desirable property to use. This first order Euler is not a recommended method for solving this differential equation system. And we can see that although error reduces as we refine the step size, it has this tendency for deviations from the exact solution to grow in an unbounded way as we go to larger and larger times. And so let's quantify. So here we now look at the error, and as far as the notation here is concerned, the 2 norm of the error is plotted in black. So 2 norm is in black, and the 1 norm is in blue, and the infinity norm is plotted in red. All right, so that's the coding for these symbols, and we have these step sizes that we use in the calculation. Every time we are halving, doubling the number of steps, and so from this number we get to 1/2 of that step size, and from here we reduce to 1/2 of that. And so we see that these errors are proportionately reducing as we reduce the step size. And we can see the same thing if we go to a logarithmic plot, which is the next plot we want to look at. So we're looking at the same data for error versus time step, now plotted in log scale. Both axes are logarithmic axes. And so we have 2 norm here, and this is the 1 norm, and the reds are the infinity norm. And you can see that if we were to draw a line here with slope unity, so this is 1 decade, from here to here is 1 decade, and here to here is 1 decade, and so a slope of 1 would simply join like that. And so that's roughly the behavior that one is observing. I didn't quite draw this as well as I could have by taking a ruler and joining to this point, and that would be closer to the slope of these data points. And so we're getting first order behavior of the error as a function of time step, but we saw previously that we have this growth of error as we increase the time horizon over which we are looking at the solution. And so that's a feature of this algorithm which is undesired, and we want to fix that. And so that is what we would want to pay attention to in solving our problems. Any problem that is given to us, we want to sort of have some anticipation as to what is the nature of the solution. Is it monotonic, or is it oscillatory with some growth or decay? And we want to choose a numerical method which is intrinsically appropriate for treating the problems that we're dealing with. So let's now look at the second order Euler on the same problem. Yeah, so we're plotting the solution here for the second order Euler stepping, and again same step sizes are used. So the number of steps are 10, 20, and 40 for the three black curves that are shown here, and red line is the exact solution, and this is second order Euler. And you can see that compared to first order Euler, the behavior is dramatically better. The solution is not showing the tendency of increasing its amplitude. It's an oscillating solution, and the amplitude and phase of the solution becomes more and more accurate as we increase the number of steps that we have, and we have better and better approximation to the analytic solution plotted as red symbols. And so we can again turn to quantify this error. So again, here we are plotting the error norms against the step size that is used. And if we want to stay consistent with the notation, we should call it delta x here. There's no time as we wrote out the original problem. We had changed notation from t to x. So error versus step size. You can see that all norms, so this is the 2 norm, and we have the 1 norm, and the red is the infinity norm. They all decrease as we reduce the step size, and they don't decrease proportionately. They are decaying more rapidly than being proportional to delta x. And so it's useful to illustrate that by going to the log scale plot. And so here we have again the error norm against the spatial step size here, and the black was the 2 norm error, and blue is the 1 norm error, and in red is the infinity norm error. And all of these errors, as we reduce the step size, reduces, and we can see that the scale here is such that we have a factor of 100 between this is 1 decade and this is another decade. And so if I were to join this point with that corner, and I'll try to do as steadily as I can, that slope would be power law 2, or proportional to quadratic behavior. And you can see that these error norms are behaving very much like quadratically. And analysis tells us that when step size becomes small enough, then we would expect analysis of the algorithm to tell us that this behavior will have this slope. When step size is large, then of course analysis doesn't apply, and so there is deviation. And so this behavior for the infinity norm, which seems to decay more rapidly here, ultimately if the step size is small enough, will also line up with that slope, and that would be an interesting thing for you to verify. So here we have now looked at this simplest possible second order ODE, which has a solution in terms of sinusoidal oscillations, cosine oscillation here for the initial conditions given, and we can show that numerically computed solution behaves in the expected way. And we saw interestingly that first order Euler is not a good method for oscillatory problems, and other methods are better. Second order Euler works quite well, but there are other methods, for example Runge-Kutta methods, Runge-Kutta second order, third order, fourth order. Fourth order Runge-Kutta is a very good choice for general problems, and in fact can be implemented with automatic time stepping and so on to control the local error and so on. And such ODE integrators are available within MATLAB or other problem solving environments, and may want to use these with knowledge of the behavior of errors that any chosen algorithm produces.